So here we are in our second lecture for this chapter. So as we continue talking about liquid solids and intermolecular forces, we gotta see that all of them are interlinked. So the properties of the solids and liquids are gonna depend on the intermolecular forces. And like I said before, we will go deeper in intermolecular forces later. For right now, remember, it's an attraction between molecules. So with that in mind, we are gonna go and discuss surface tension and viscosity as representation of the effect of intermolecular forces, specifically in liquids. So let's begin with this problem. And you have seen this before. I know you've seen this before. A mosquito can walk on water. A paper clip can float on water even though both of them have densities that are higher than the water, and most likely you learn in middle school and high school that anything that is denser than water will sink in water. However, you don't see that happening here. Why? Well, for that we have to talk about surface tension. So as this says, if I have something like a liquid, this would be the surface, and there's some tension to it, there's a force to it. So let's look deeper into this zone. So if we're talking about water, we know that water is a polar molecule with a bent shape. And we know that it's also a dipole because it tends to be partially negative to the top because the electrons are being pulled that way. The electrons that are shared on the bonds, and they combine to give you an overall force like that. And because of that, the electrons which are negative are going to be toward the top, and the bottom will be kind of lacking electrons, and that will make it electron deficient or partially positive. And therefore, like I mentioned before, we have two poles which make this a dipole. So on the surface of a liquid, I'm going to have a water molecule attracted to another water molecule. The partially negative is attracted to the partially positive of another water molecule. So we're going to have that attraction right there. So they're attracted to each other. And I'm going to keep observing that on all the water molecules that are on the top of the liquid, on the surface of the liquid. And then as we go deeper into the liquid, we're going to see other water molecules. And they're going to be attracted to other water molecules. So they're going to be attracted everywhere they can find a partially positive and a partially negative. And we're going to have other water molecules. And they're going to be attracted to other water molecules and to others like that. So everywhere they can align a partially positive with a partially negative, it's going to be like a magnet. If you notice, if we amplify this a little bit, if you notice, for example, this water molecule is feeling attractions all around it. However, the ones on the surface only feel attractions underneath them. There's nothing attracting them on top. There's no water molecules on top, obviously, that's the surface. That makes these water molecules depend on this force in here also, forming what we can virtually call a layer. And that layer, if you try to push on it, as long as these forces hold, that layer is going to hold. Like I told you before, if I'm playing on a trampoline, every time I drop into the trampoline, it's kind of going to bend a little bit, but it's going to resist my weight because it's a tension between the parts. But if I happen to put too much force in there, because suddenly all my body gets bigger, then these forces will break and I will fall through because I broke the surface. So that's a phenomena we observe in liquids. As long as the weight of the mosquito is not bigger than the forces that are holding the molecules together, they're not bonded, they're just being attracted like a magnet, the mosquito will hold in there. As long as the molecules on the surface underneath the paper clip are holding together, the actual weight of the paper clip is not enough to push it down like I would push through a trampoline if I was extremely heavy compared to the force of the trampoline. But if I suddenly place my finger in there and I put pressure down, the paper clip will definitely go to the bottom. And you can, if you don't believe me, you can try yourself, right? Very careful, take a paper clip and place it on the water and you will see how it floats. Any sudden push will break that force. So that's what surface tension is. It's a phenomenon we observe due to the fact that the molecules on the surface do not have as many attractions as the ones below, so they tend to make like a layer in there, which can easily break with some extra pressure there. So that's how we can visualize and define surface tension. What about something like this? What about an experiment that we did here? We took 5 different liquids, we put it on test tube, and then we turned all of them at the same time. And we see a lot of liquid coming out of this one. This one, you see some liquid coming. This one is barely coming out, basically one drop, while all these have come out already. And these ones are not even coming out. You're gonna have probably tap on it. It's just like having a bottle full of water and a bottle full of ketchup, for example, or maple syrup, and you turn both of them around, the water will empty right away. It will flow right away. So how can we explain that? How can we explain the behavior of these 5 liquids? The force that is pulling there is gravity, is the same for all of them, but they're coming out not at the same speed. And what we're saying is that the molecules are not flowing with the same speed. So how can that happen? Well, let's say that I have a molecule of a liquid and another molecule of a liquid, and this one had to flow past that one. And let's say that when it's flowing through, there's an intermolecular force that catches on, and it kind of bring them together. So as the molecules is trying to flow by, it gets caught up because of this intermolecular force. And the bigger the molecule, the longer it's going to take to flow by. If we have other molecules, when these begin to flow by that molecule, there's going to be intermolecular force, but it's going to be smaller or weaker than the other one, so it will flow faster. That's what we call viscosity. So viscosity is a measurement of how fast molecules can flow past each other. The stronger the intermolecular force, the more they're going to tend to stick together and the flow will be diminished. That's what that we are observing here. The intermolecular forces are very strong here, so the molecules want to stay together. They don't want to flow past each other. In here, the intermolecular forces are very weak compared to that one, for example, and the molecules are just passing one another without even saying goodbye or hello. So intermolecular forces are gonna diminish how fast a molecule can flow past each other, therefore creating a higher viscosity. Another thing that can affect viscosity is the size of the molecule. For example, imagine I have a molecule that is like this, and there's another molecule that is like that, and it's trying to flow by. Intermolecular forces will hold it. But in addition to that, something like this can happen. If you have a molecule like this and another molecule like that is trying to flow by, they probably can do something like this. And they can entangle together. And if they entangle together, the eventual flow of one molecule past the other is going to be harder. And that's going to create also a higher viscosity. The example I always like to do is, if you are cooking pasta and you're cooking elbows, let's say, and you put your spoon in there to shake them or to mix them, it's going to be kind of really easy to mix your elbows on your pasta. But if you have a bunch of spaghettis and you try to put your spoon in there, it's going to be kind of harder to stir the spaghettis because they're entangling each other. So you can use that analogy to explain viscosity. So viscosity is going to be affected by two factors. First one, the strength of the intermolecular forces. Imagine intermolecular forces are like glue. The more glue you put in two pieces of paper, the harder it's going to be to get them past each other. So that would be the intermolecular force analogy. The other one is the size of the molecule. The longer the molecule, the more the possibility that they will entangle the same way spaghetti entangles when you compare them to elbows. And if you visualize those two those way, at least until we learn more about intermolecular forces, you can explain viscosity to a 6-year-old. So keep that in mind. So to put that into practice, go ahead and do this daily work. Redefine on your own words. Do not copy and cut anything from the internet. That doesn't do anything for you or for me. So try to put it on your own words. Work through it. And explain what surface tension is. And thinking about intermolecular forces, how does it depend on it? The surface tension gets stronger or weaker, the weaker or stronger the intermolecular forces are. And once you do that, do the same with viscosity. How does it depend on intermolecular forces? And you can even throw some size and entanglement in there. And what is viscosity? So once more, I am not interested in seeing a definition that I see everywhere I open the internet. I can even ask Alexa, she's probably listening to me. Work through it and put it on your own words. That have a lot more value for me. So when we come back, we will have said that we understand now surface tension and viscosity in relation to the intermolecular forces. So when we come back, we will be talking once more about intermolecular forces and how it relates to the changes of phases or phase changes in relation to evaporation and condensation. And we're going to see, going back to what we learned on chapter 3, a new way of calculating the energy involved in those processes. And we will do the same later for melting and freezing. So until the next one, let me leave you now with viscosity and surface tension.